Pluto, a mysterious dwarf planet and the looming orbital puzzle. Pluto is a mysterious dwarf planet that lives far away, once considered part of our solar system's planetary group. Although it was reclassified, recent unexpected announcements made by prominent physicist Neil deGrasse Tyson and others have brought Pluto back into the spotlight, thanks to a shocking discovery. They suggest that this icy world may be on a possible path of collision with Neptune. But what caused this, and what consequences could it have? Are we witnessing a rare astronomical phenomenon, or is there more to this looming cosmic clash? Join us as we investigate the potential effects of a Pluto and Neptune encounter. Pluto was once classified as a planet but was partially reclassified as a dwarf planet due to its peculiar orbit. Nevertheless, it remains a subject of intense interest and investigation in the astronomical community. According to recent predictions from renowned scientists, Pluto's path is dangerously close to Neptune's. Neil deGrasse Tyson, along with other experts like Kaku, has raised concerns about a potentially dangerous collision between the two, which could constitute a serious threat to Earth. But what makes such an event even conceivable? Pluto's orbit around the Sun is unlike any other in our solar system. It takes an incredible 248 years to complete one orbit. Since its discovery in 1930, Pluto has not yet completed one full revolution. However, the fascination does not end there. Pluto's high gravity traces an elliptical path that significantly departs from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination. The orbital path tilts 17 degrees to the ecliptic plane, much steeper than those of the other planets. This elliptical and inclined orbit adds complexity to Pluto's behavior in space. One of the most fascinating features of Pluto's orbit is that it intersects Neptune's. For approximately 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune does, defying our expectations based on their distance from the Sun. Naturally, we ask, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. Soon after Pluto's initial discovery, astronomers began studying its orbit. Unlike other planets with relatively flat orbits, Pluto's steep and elliptical path stood out. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's. Despite this, Pluto remains in a stable orbit, evidence of the complexity of space mechanics. The so-called three-body problem helps explain how celestial bodies like the Sun, Pluto, and Neptune move and influence each other through gravity. It's similar to trying to predict where three objects will go, based solely on their current positions and mutual interactions. This issue reveals the intricacy of Pluto's orbital path and how it interacts with Neptune and the Sun. Terms like vibration and latitude are components of what's known as the VSSK oscillation. According to astrophysicists, this phenomenon helps explain what holds planets in their orbits. When Pluto enters the region near Neptune's orbit, it is always at least 90 degrees away in position. This spatial separation prevents a collision. The vibration of latitude, on the other hand, refers to the vertical movement of an object within its orbit. For Pluto, this means that even when it's at its closest to Neptune or another massive planet, it remains far above or below their orbital planes. This adds yet another layer of protection against collision. Another key concept is the VSK oscillation, named after scientists von Sippel, Kai, and L.V., who studied the gravitational interactions of three-body systems. Pluto, Neptune, and the Sun rely on one another's gravity to maintain orbital stability. In Pluto's case, the VSSK oscillation helps explain why its course around the Sun remains stable despite its unusual path. Even though the orbit seems chaotic, this oscillation ensures that Pluto continues on a consistent route over long periods. Pluto's orbit is held in a stable pattern that prevents it from hitting Neptune or being lost in space. The three-body problem further aids our understanding of how gravitational pulls change and influence each object's motion. Another benefit of studying Pluto is that it provides insight into how distant worlds behave in our solar system. Simulations from the 1980s revealed that Pluto's orbit is technically chaotic. Small changes in initial conditions can lead to drastically different outcomes over millions of years. However, these same simulations also demonstrated that Pluto's orbit retains equilibrium for extraordinarily long timescales. Recent computer models show how massive planets like Jupiter and Saturn influence Pluto's path. There's a special relationship between Neptune and Pluto. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This orbital resonance helps keep Pluto's path steady. But Neptune isn't the only helper. Jupiter's gravity plays a significant role in maintaining Pluto's secure orbit, with some assistance from Saturn as well. These findings demonstrate that even in the chaos of space, Jupiter alone has enough gravitational influence to keep Pluto's course stable for billions of years. Such gravitational phenomena play a crucial role in the broader cosmic context, maintaining predictability and order in planetary movements. Without these stabilizing mechanisms, our solar system would be more disordered and unpredictable. Bodies like Pluto could be thrown into collision courses or ejected from their paths, causing chain reactions. In discussions about the potential for Pluto to crash into Neptune, its orbit becomes a case study in the fluid nature of solar systems. Even the most unstable orbits can reach a balanced state due to complex gravitational interactions and orbital mechanics. Moreover, the need for constant observation and investigation becomes clear. Exploring the depths of space often forces us to confront the unpredictability of celestial bodies, and Pluto's orbit is a prime example. The concept of orbital chaos, where tiny changes in initial velocity or position result in wildly different long-term paths, is well illustrated in Pluto's case. Computer simulations have been vital in tracking Pluto's trajectory. By altering just a few variables, astronomers have seen massive impacts on Pluto's projected location. These simulations, started in the late 1980s, revealed a striking truth. Despite chaotic tendencies, Pluto's orbit remains stable across billions of years. This long-term stability, amid apparent short-term chaos, highlights the subtle order in our universe. Predicting cosmic events, especially involving erratic orbits like Pluto's, is an enormous challenge. Even with sophisticated simulations, results are heavily dependent on accurate initial conditions. A minor error or oversimplification can lead to completely different outcomes. Thus, while numerical simulations help us understand and predict the movements of celestial bodies, they also remind us of the universe's inherent unpredictability. Pluto serves as an example of how much we still have to learn. Studying how massive planets like Jupiter, Saturn, and Neptune affect Pluto's orbit offers invaluable insights into solar system dynamics. It shows how one planet's position and presence can ripple through the system, influencing the paths of others. So why are prominent astrophysicists like Neil deGrasse provides valuable insight into how scientific consensus evolves and why Pluto remains a subject of intrigue and debate. Tyson's role in reclassifying Pluto was based on scientific criteria, specifically, its inability to clear its orbit of other debris, a key requirement for planethood under the International Astronomical Union's 2006 definition. Yet, despite the demotion, Pluto has never faded from scientific attention. In fact, it has gained renewed relevance due to the unique characteristics of its orbit and its relationship with Neptune. The current concerns raised by Tyson and others are not grounded in a literal prediction of an imminent Pluto-Neptune collision, but rather in how this situation symbolizes the delicacy of orbital mechanics in the solar system. While Pluto's orbit does cross Neptune's from a two-dimensional viewpoint, in three-dimensional space they are protected from collision by a stable 3:2 orbital resonance. This means that for every 3 orbits Neptune completes, Pluto completes 2, ensuring they never come dangerously close. Furthermore, Pluto's 17-degree inclination from the ecliptic plane, combined with what's known as orbital precession, adds layers of temporal and spatial separation from Neptune. This intricate dance is a testament to the resilience and stability of celestial mechanics, refined over billions of years. It's not a coincidence but a cosmic arrangement of balance, similar to how Lagrange points maintain the relative positions of other space objects. Astrophysicists highlight this as a classic case of chaotic stability, a condition in which a system may appear unstable or unpredictable on small scales but remains balanced over incredibly long timescales. The long-term computer simulations, many developed since the 1980s, consistently show that Pluto's orbit is stable for millions to billions of years, even when taking into account perturbations from other gas giants like Jupiter and Saturn. However, the significance of this topic extends beyond planetary collisions. The orbit of Pluto challenges our understanding of what constitutes a planet, how we define orbital zones, and the long-term fate of small bodies in the solar system. It opens questions about the Kuiper belt, where Pluto resides, and the many other icy bodies whose gravitational interactions remain poorly understood. The notion that Pluto could somehow collide with Neptune reflects more a metaphorical concern, a cautionary tale about how small shifts in gravitational dynamics, potentially triggered by external influences like rogue planets or close-passing stars, could disrupt what we assume is stable. In this sense, the discourse surrounding Pluto becomes less about a specific event and more about the fragility of cosmic systems. As Tyson and other astrophysicists continue to raise awareness, the goal isn't fear, but curiosity. Understanding Pluto, its wild, tilted, resonant orbit, invites us to consider the deeper workings of the universe, where chaos and harmony are often indistinguishable, and where the smallest objects may offer the biggest insights. Commentary on the way in which the public's fascination, and the mechanics of the heavens, intersect with the uncharted territories of space brings us to Tyson's position regarding Pluto. The foundation of Pluto's reclassification lies in our ever-growing understanding of the solar system. Tyson doesn't view the reclassification as a punishment but as a necessary adaptation to our expanding knowledge of the many objects that orbit our Sun. The way Tyson approaches the mechanics of space is one of ongoing education and adaptation. He recognizes the difficulties of orbits like Pluto's, which serve as a reminder of how much remains to be discovered. The enchantment of these uncertainties, particularly the dynamic interactions between Neptune and Pluto, highlights the unpredictable and ever-changing nature of our solar system. His work emphasizes the idea that the more we learn, the more questions arise, encouraging us to investigate and refine our comprehension of the universe. Michio Kaku, another well-known futurist and physicist, provides a unique but complementary perspective on space's mysteries, focusing on the unpredictable forces that shape the universe. Kaku is known for his ability to connect disparate concepts rooted in science and futuristic vision, making him an important voice in discussions about the mechanics of the universe and its broader implications for humanity. His perception of Pluto and its orbit emphasizes the necessity of continuous observation and sophisticated modeling to recognize and anticipate potential cosmic events. He sees the interaction between planets and stars as crucial, not merely for academic purposes, but for their practical implications. Pluto's potential collision with Neptune, for instance, is not just a speculative scenario, but a reminder of the fluid and frequently chaotic nature of space. Kaku's futuristic outlook inspires us to consider the broader repercussions of such events and their effects on our understanding of the solar system and the potential need for future space interventions. From his perspective, being prepared for the unexpected in space is essential. His work suggests that the more we understand the forces at play, the better prepared we'll be to navigate and possibly mitigate the negative effects of cosmic events. Tyson and Kaku's points of view converge on the notion that space is a realm of unending exploration. Despite its vastness, our current understanding remains limited. Both emphasize the importance of continued investigation and advanced modeling in space science. They draw attention not only to comprehending the current mechanics of the universe but also to anticipating their potential future shifts. The possibility of a collision scenario involving Neptune and Pluto serves as a symbolic case for the larger opportunities and challenges in space exploration. It emphasizes the need for robust research, cutting-edge technology, and the flexibility to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, as revealed through Pluto's orbit, are a call to scientific action, urging both the scientific community and humanity to extend the boundaries of knowledge. There is general agreement among scientists that, in the near future, the orbits of Neptune and Pluto will remain stable due to their slow movement, orbital resonance, and a variety of gravitational influences. As a result, a direct collision between Pluto and Neptune is considered extremely unlikely. However, the complexities and potential disturbances in orbital dynamics mean that astronomers must remain vigilant, continually observing and analyzing these celestial bodies to understand their behavior over time and assess any risks they might pose. In contrast, while a Pluto-Neptune collision remains speculative and unlikely, its consideration underscores the significance of continued research and advances in observational astronomy. New technologies, such as advanced telescopes and more accurate computer simulations, will help improve our models and predictions, allowing humanity to stay informed about our solar system's constantly changing nature. Tyson's perspective on Pluto's reclassification and Kaku's focus on the unpredictability of celestial mechanics both reinforce the necessity for continued exploration and adaptability in our understanding of the universe. The hypothetical collision scenario underscores the complex and dynamic interactions within the solar system and reminds us of the still uncharted horizons in our pursuit of cosmic knowledge. Through ongoing research and observation, we aim to uncover these mysteries, ensuring our understanding evolves alongside the ever-changing universe. The study of Pluto's orbit also opens up broader discussions about the solar system's overall stability. The relationship between Pluto and Neptune is particularly fascinating due to the gravitational interactions that govern their paths. Every celestial body, whether moon, planet, or dwarf planet, exists in a delicate balance. Their movements and positions often interact in ways that appear paradoxical. This complexity challenges our assumptions about what is stable or unstable in space. Astronomers continuously confront the difficulty of making long-term orbital predictions, as even minute changes can echo across space for billions of years. Despite Pluto's initially unpredictable path, cosmic forces ensure these bodies remain in harmony over vast timescales. Yet even a slight change in a planet's orbit, or an unexpected gravitational pull from another body, could disrupt this balance. Such a disturbance might shift the trajectories of planets, moons, or even contribute to the formation of new dwarf planets like Pluto, causing ripple effects throughout the solar system. Therefore, it remains crucial for scientists to keep refining their models and studying the movements of these distant worlds, ensuring readiness for unexpected cosmic shifts. This ongoing observation brings us closer to a deeper, more comprehensive understanding of the universe. In addition to scientific preparedness, both Tyson and Koku advocate for cultivating a mindset of curiosity and resilience. The unpredictability of celestial mechanics, like Pluto's orbital behavior, is not a source of fear, but rather a catalyst for deeper inquiry. These uncertainties challenge us to enhance our methods, broaden our theories, and remain intellectually agile as our tools for exploration improve. Space, as they present it, is not a static arena, but a living, evolving expanse of possibilities. With every new piece of data, whether it's from telescopes, probes, or simulations, we are not merely confirming what we know, but often overturning assumptions long held as truth. The redefinition of Pluto's planetary status is emblematic of this process, an example of science's willingness to self-correct, to admit its limits, and to grow beyond them. Moreover, Tyson emphasizes that public understanding plays a crucial role in the advancement of space science. The fascination with space must be coupled with education, turning awe into awareness. When the general public understands why Pluto was reclassified, or why orbits behave the way they do, it fosters support for scientific endeavors and funding for missions that deepen our cosmic knowledge. Koku, on the other hand, often extends the implications of space unpredictability into future scenarios, ranging from interplanetary travel to planetary defense. His forward-looking approach suggests that what we learn today about orbital resonances or dwarf planets might one day be the key to protecting Earth from asteroid impacts or guiding human colonies across solar systems. In both perspectives, the central message is clear: knowledge is not static, and our understanding of space must evolve with every new discovery. Whether it is Pluto's eccentric orbit or the vast forces that keep Neptune in harmonious resonance, every aspect of celestial motion invites us to look closer, think deeper, and imagine farther. As we develop better instruments, both observational and theoretical, the questions we can ask grow more sophisticated. We are beginning to map gravitational waves, detect exoplanets with increasing precision, and simulate entire star systems with artificial intelligence. This marks a transition from mere observation to predictive modeling, where the mysteries of the universe become slightly more knowable. Yet, the greatest challenge lies not in the technology, but in maintaining the spirit of exploration. Tyson and Koku exemplify two distinct but overlapping philosophies, one grounded in rigorous scientific explanation, the other reaching toward visionary possibilities. Together, they represent a balanced approach to the future, one that respects the mechanics of the present and prepares for the disruptions of tomorrow. In the end, the discussion of Pluto's status, Neptune's gravitational dance, and the intricate choreography of our solar system is more than academic. It is a reflection of humanity's drive to understand its place in the cosmos. And as long as questions remain, as they always will, the pursuit of answers through observation, modeling, and imagination must continue.